Alright guys, hope you guys are keeping safe. So this is a requested video by Elise asking about page 5, question 3. So for us from your book over here, like some of these questions can be very confusing. So if you get confused, just send me an email, and then if it's simple, and I'll just send it back, reply right back to you. If there's any question that you want me to explain it, just let me know, and I can make a video out of it. And because I'm under quarantine at home anyway, so I have quite plenty of time. So yeah, so if you're confused with it, probably other people are confused as well. So shout out to Alice who sent this video request out. So yeah, so I'm gonna talk about this question for you guys. All right. So what we have over here is we have a flywheel, and then this flywheel have a stick coming out over here. Okay, and then there's the axle, so there's a load over here. Okay, so what do we know? We know a heavy flywheel of mass 15 kg. So this object is 15 kg. Okay, and then it has a radius, that's the radius. The radius, I'm gonna use a capital R right over here. The capital R is gonna be 20 centimeters, so I'm gonna write 0.2 meter. Okay, 0.2 meter. All right, and then it has an axle. Axle is over here. It's a little r that equal to 0.01 meter. Okay, and negligible mass. So we're ignoring the mass of this thing. So basically that is the rotating part. Okay. All right, and then a cord one of the axle sits hanging vertically, this on the ground, and the load is released from rest. And this object is going to be accelerating downwards with 1.25 meter per second squared. Okay, so this question is very similar to the question I've talked about the other day, which is the question 5. Okay, so that's the difficult one. Okay, we're going to have a look of this question as well. Say first, calculate the rotational inertia of the flywheel given the rotational inertia of a solid. This is this. All right, so that's pretty straightforward. We just use the equation. Well, rotational inertia equals to half mr squared. So put the number n, half. The mass is 15 kg over here, and then the radius, we're going to be using this radius because that's where the actually mass is distributed. Okay, so not this axle, it's a big one. Okay, so and then we're going to times 0.2 squared. Okay, so we'll put that in the calculator. 0.5 times 15 times 0.2 times 0.2. Okay, so that gives me 0.3 kg meter square. Okay, that's units from that. Okay, and then let's look at the question B. Draw a diagram showing the forces acting on the load while it's falling. Okay, so the load while it's falling, that is gravity going downwards, and then there will be a tension force going upwards. Again, because object is accelerating downwards, so the tension force will be a bit smaller. Tension force, right? Okay. So number C, draw a diagram showing the forces acting on the wheel and axle while the load is falling. Okay. So over here on the axle, I'm going to use a green pen. There is only one force acting on the axle, and that is the tension force pulling it downwards, making it rotate. And this tension force will equal to this tension force over here. The two tension forces will equal to each other. But gravity does not equal to tension force because some of gravity is going to be used for acceleration. Okay. All right. So now calculate the angular acceleration of the flywheel. Okay. B and C, we've already done that. So now we're going to come to D. The angular acceleration of the flywheel. Well, if I have linear acceleration, I can turn the linear acceleration to rotational acceleration. So A equals to alpha R. So the alpha is going to equal to A over R. Put the numbers in. 1.25 divided by 0.01. So it's going to be 125 rad per second squared. Okay, because the object's linear speed equals to the linear speed of this rotating axle over here. And then that can turn into that rotational speed over there. Okay, let me see, did I write it right? A equals alpha r, alpha equals a divided by r. Okay. Okay. Sweet. So then the next part, okay, calculate the torque acting on the axle. Okay, so the torque acting on the axle. So, this question is the opposite from question 5. So actually they've given us inertia. If we know inertia here and we know the angular acceleration, so now we can actually find torque. So torque equals to I alpha. So that equals to 0.3 times 125. Right? Okay, sweet. So now we can put this into the calculator. 0.3 times 125. 37.5 Newton meter. Okay, so that is going to be my torque. And where does this torque come from? The torque coming from the tension force over here. So let's go have a look. Okay, question F. Going to ask us about the tension force now. Okay, torque equal to the tension force times the radius, which is a little r. Okay, so now 370.5 is going to equals to tension force times 0.01. So the tension force is going to equal to that 37.5 divided by 0.01. That'll give me 3750 Newton. 3700. Well, the number is quite big. I wonder if I calculated wrong somewhere. Let me just quickly check. This torque and acceleration, question 3. Torque acceleration, question 3. Oh yeah, it's correct. It is a big number. Okay, so now question F and G. Question G is to calculate the mass of the load. Okay, and then we go, well, there is a tension force going up, which is this. So that equals to 3750 Newton. That equals 3750 Newton. So if we want to know the mass there, so we can use gravity. Gravity equals to mg. And then we do a force analysis on this object over here. Okay. So the net force is going to equal to the gravity force minus the tension force. And that is going to create a mass acceleration. Okay. And then we put the numbers in. Okay. So it's, I just use 10 times mass minus 3750 equals to 1.25 mass. Okay, and then I can rearrange. So 8.75 mass is going to equal to 3750. Now mass equal to 3750 divided by 8.75. Okay, and then I can put that in the calculator. 428 kilogram. All right, so that's how you do this question. I hope that makes sense. If you have any question, just send me an email and let me know. Cool. All right, have a good day. Stay safe.